Hello everyone. You should be able to hear me. I've prepared some exciting problems for you today. Yeah, um, we're going to talk about integration, Riemann sums. We're not going to talk about integration yeah, just Riemann sums, and we're going to talk about center of mass, of course. So it's a mixture. It's a mixture of physics and maths. But if you've seen the physics and math assignments, you will realize that they are really similar. They're based on the same topic. So I'm going to share my screen. I am excited. I love this topic, honestly. So screen 2, yes. You should be able to see my screen. If you can't, please let me know. And right, so get ready for some exciting stuff. So first, the concept of Riemann sums. So what are Riemann sums? Who thinks they understand Riemann sums on a, or at least have a, if you type 1 if you think you have a good understanding of Riemann sums, and 0 if you think you don't have a good understanding of Riemann sums. It's okay to type 0. So if you, a lot of ones, some 0.5, okay. 0. Anything else? A Riemann sum. What is a Riemann sum, and what are the? It's, well, it is. Yes, in a way, it is the sigma. So it's based on the definite integral, and if you look at a graph, if you look at a graph and you draw it like this, let's say you want to find the area between two points A and B, and what you do is you say, okay, I don't know how to calculate the area under the curved graph, but I'm going to draw a rectangle like this. Then I'm going to draw a rectangle like this. Then I'm going to draw a rectangle like this, and like this, and like this, and like this, and like this. And the total area of the rectangles is approximately equal to the area under the curve. If this is x, let's say this is x1, this is x2, this is x3, etc. I am using, for the height of the rectangle, I'm using f of x1, then again f of x2, etc. So the area, total area of rectangles. Let's assume that the width of one rectangle is delta x. Total area of rectangles is, so for the first rectangle, A1, we take the height of the rectangle, which is f of x1, and multiply it by delta x, by the width. So plus f of x2, delta x, plus etc. So we need to add all of them. And we can shorten that to saying, well, it is the sum of f xi, where I changes from 1 to n delta x. And this is called a Riemann sum. What we do next is we make the rectangles narrower. Let's look at an example. So this is a Riemann sum tool. So I've got a curve. I got a curve here. And I'm saying approximate the area under this curve. So the curve is from 0 to 3. Approximate it with 2 rectangles. And you can see that the first rectangle is this, and the second rectangle is this. The estimated area is 19. The actual area is 27. So we have an underestimation. If I use 4 rectangles, I get closer to the actual area. The actual area is 27. The estimated is 23. If I use 8 rectangles, I get even closer. And with 16 rectangles, I wonder how many I can do. What if I do 128? Ooh, 26.9 and 27. So really, really close. So this is what I'm doing. I'm making the rectangles narrower. And the area, so the total area of rectangles, the area under the curve, area under curve, which is not the same as the total area of rectangles, is equal to the limit of this expression, the limit of I, of fxi, delta x. I'm not putting n here because n changes as well, curve, as delta x tends to 0. So as the width of the rectangle becomes 0, this becomes the integral from a to b of f of x delta dx. Sorry. So you can see the similarity. Look, the sigma becomes the integral. F of x, well, f of x is f of x. And delta x becomes dx. So delta x is a change in x, and dx is an infinitely small change in x. So we are slicing, we're literally slicing the area into very, very thin parts and trying to establish the area. Okay. Hopefully you understand. Hopefully you understand everything. So can I get a vote on a 0 to 10? How well do you understand what I've done? Okay. All right. So, okay, you've come ready. You've come ready for this stuff. Okay. Can I ask, Archie, which part do you find confusing? You can use the mic, or you can use the chat. Which part would you like clarification on? Sorry to. Well, I is the order because we go x1, x2, x3, etc. So that's why I said xi, xith. X1 is a, yes. Okay. Yes, so one is a. Usually it's x0, but it doesn't really matter in this case. I'm trying to do the concept, and let's do something very familiar to you, but let's do it using Riemann sums. So I just want to show you how to use the Riemann sums. Find the area of a circle by slicing it into strips. Now, find the area of a circle by slicing it into strips. Okay, so let's take a circle. Okay, too big. That's fine. And I'm going to slice it, but I'm not going to slice the whole thing. I'm just going to take half the circle. I'm going to take half the circle and slice it like this. They should be the same width though, so I've just slightly messed up, but it's not the point. Okay. Approximately the same width. Now I need the equation of the circle. So if this is x and this is y, and this is x and this is y, then you need the equation of the curve. And we know that the circle has equation x squared plus y squared equals. Now, do I want to make the circle of radius 1 or do I want to make a circle of radius r? Okay, let's try circle of radius r. It makes maths a little bit more complicated, but hopefully you'll catch up. So r, radius r. Just the result is more exciting when you do it with r, although the calculations are complicated. So this is 0 and this is r, and you can express y. Y is square root of r squared minus x squared. Okay, so we got y. We need the rectangle. So let's take this rectangle. Let's take this rectangle, just one from the middle, and look at it closely. Like take a single rectangle. The width of this rectangle is delta x. Delta x, and the height is 2y. Yeah, does that make sense? Because if this is the equation of this line is y equals square root of r squared minus x squared, so this is y, this is the y, so the whole height is 2y. So area is 2y delta x. Okay, so area is equal to 2 square root of r squared minus x squared delta x. And the total area, of course, total area is the integral, is the sum, sorry. So total area is approximately the sum of 2y delta x, I from 1 to n. So it's the total area is the sum. So we can simplify that and write down 1 to n, 2 square root of r squared minus x squared delta x, where this is xi, this is the ith, this is the square in the xi. Xi is the position and this is yi. Hopefully that makes sense. Now the total area so I forgot the 2. I forgot the 2 because we only did half a circle, so we need 2 of these circles. So 2. So total area is going to be is the limit of that, is the limit as delta x tends to 0 of this expression of 2 sum I equals 1 to n 2 square root r squared minus x I to delta x, which is equal to, and the limit of that is equal to the 2 times the integral from 0 to r of 2 square root of r squared minus x squared dx. So delta x becomes dx. All right. So area of a circle. Is. Now we take the 2 out, so it becomes 4. 4 integral 0 to r. Now square root of r squared minus x squared dx. Now this integral is done by substitution, and the substitution is quite unusual. The substitution is well, one way of doing away substitution. This is done differently, but it's okay to look up difficult integrals. Okay, as I said, integration is such a vast topic that it's almost impossible to know everything. So if you're not sure how to integrate, you can look it up. Okay, unless, yeah, it's r sine theta. This is the substitution, and we just use the result. Which we can interpret here. So we can put it as, so 4 multiplied square bracket, so x square root r squared minus x squared over 2 plus a squared over 2, r squared over 2, sorry, it's r squared over 2, arc sine x over r, between limits 0 and r. Now, hopefully, if I haven't messed anything up, we'll see something almost magical happening. So we substitute r, and as you can see, r is going to be, okay, it's 4 r square root of r squared minus r squared divided by 2 plus r squared over 2 arc sine r over r minus, now we substitute 0. Well, that's an easy substitution because this is 0. And this is arc sine 0 minus, this is r squared minus r squared over 2 arc sine 0. And arc sine 0 is 0. So this is 0, this is 0. So we're left with 4 multiplied by r squared over 2 multiplied by arc sine 1. And arc sine 1 is pi. And so it's 4r squared over 2, 4r squared over 2 pi. Where did I mess up? I have messed up somewhere. Pi over 2, of course. Arcsine 1 is pi over 2. Yes, pi over 2. Okay, so small mistake. Arcsine 1 is pi over 2, which makes it 2 cancels pi r squared. A result which shouldn't be of any surprise to you. It's an area of a circle, and we've sliced it into strips. And that's what we've done. That's how we've used the Riemann sums here. So we started by writing them with, what's the calculation without the integral? Well, but what do you mean? I mean, how would you not use the integral here? Just this, well, the sum, yes, but I mean, you can't do the sum because it's a sum of an infinite number of things. So you have to use the integral. In the assignment, can we use the internet to look up such integral? Yes. In short, yes. Unless we ask you to find the integral. I mean, if it's an integration question, it says integrate this. Of course, you can't use the result. You can look it up and get some help from there. Yeah, we're not limiting you to. You don't. You can use any resources you like, as long as you can explain how to get there. Okay, so that's that. I mean, the search for solutions is a lot. Is an important thing as well. Of course, nowadays it gets easier and easier to find the correct solutions. So make sure you don't lose yourself on the way. If the width of the rectangles were given, well, yes, you could add them, but you would get an overestimation or an underestimation. You won't get the exact value. If you get 10 rectangles, of course you can calculate well, let's do it. Like, let's do the actual thing. So it's going to be square root. So let's take a radius 1 minus x squared to the power 0.5. And we need 4 of them. So 4 times that. X goes from 0 to 1 using 10 rectangles. And that would give you a radius of, the actual area is 3.14. So it's pi, but because it's pi r squared, pi times 1 squared. But the estimated area is 3. So 3.3. So you wouldn't get the exact result by adding. Of course, you can add. Okay, so all right, we're slicing it into strips. Let's do the same question, but in a different way. Find the area of a circle by slicing it into concentric, I can't spell, concentrical rings. So now we have a circle. Let's make it neater. We have the same circle of radius r, And we're going to slice it into rings. Isn't that just the neatest concentrical set of concentrical rings you've ever seen? Right, so etc. If this question says to use Riemann sums, you need to set up a Riemann sum. Look, using a Riemann sum, it follows here. This is a Riemann sum. This is a Riemann sum. And the integral is simply the limit of the Riemann sum. Right? So this is a you go from a Riemann sum to an integral by setting the limit of delta x to 0. So the Riemann sum gives you an approximate area. The integral got Archie, you're asking a difficult question. How do you find that the anti-diffraction gives you the area under the curve? I forgot the answer to that question. I've been so busy doing integration that I forgot. I'll have to look it up. It's a very good question. Thank you. I'll write it down for myself. Y is to area. Yeah, I don't have the immediate answer. I thought the limit was delta x gets to 0. Yeah, delta x gets to 0 because the width of the rectangle decreases. Yes, the limit was set. Yes, so when you set the limit, the Riemann sum becomes the integral. So the sigma becomes the integration symbol. Delta x becomes dx. And now you have something very familiar to you, which you can integrate. Well, not particularly this integral. This is a difficult integral. I'm not expecting you to know how to do this one. Okay. So looking at concentrical rings, we want to find the sum of the area of the rings. So to find the sum of the area of the ring, let's look at one ring. So one particular ring, let's take this one. Doesn't matter which one, just an arbitrary ring. I'm very much a physicist and less of a mathematician. So I was always interested in the practical application. Like finding center of mass is a practical application, whereas pure maths is wasn't always my cup of tea. So let's take a ring, and let's take a ring of radius r. Well, it's the ith ring. So if you number the rings, number 1, 2, 3, 4, and this is ring number I, and the ring number I has radius ri. So let's get it out. So this is the ith ring. Okay, and it has a radius of ri. Let's say the width of this ring is delta x, delta r, sorry, delta r. Now, so what is the area of this ring? So because assuming delta r is small, we take this ring and we unwrap it into a strip. Yeah, if you take the ring, it's like a hula hoop. You can make it straight, you straighten it out. So what you do is you say, well, would you look at that? I can make this ring into a strip. And the width of this strip is delta x. And the length of this is 2 pi r I. Yeah, the function itself is the derivative of the area. Ah, yes. Yes, I see what you mean. Yeah. So you can go from there. Okay. So we take this ring and we literally just unwrap it. And now the area is 2 pi ri delta r. Sorry, delta r, not delta x. Okay, and the total area, um, total area is the sum of all the rings. So I from 1 to n of 2 pi ri delta r. And well, that's cool. Is approximately, of course, total area is approximately this, because area is approximately this. And now we can say the area is equal to, now we do the limit of delta r tends to 0 of this sum 2 pi ri delta r, which is the integral of 2 pi r dr. And now the limits from 0, we go from 0, the radius changes from 0 to r, which is the radius of the big circle. So radius goes from, the smallest circle has a radius 0, the biggest circle has a radius r. And now we integrate this, so 2 pi goes out. And now the integral of r dr from 0 to r, and of course this is 2 pi squared, so it's r squared over 2 from 0 to r, and we substitute r, so it's 2 pi r squared over 2, 2 cancels, and we're left with pi r squared. Would you look at that? It would, but if we take a very, very thin strip, it would pretty much have the same, the bases would be the same. So if we take a trapezium, of course it would be trapezium, but as this is A and this is B and this is delta R, as delta R tends to 0, A tends to B and B tends to A. So it doesn't actually become a rectangle, it just becomes, the area of the trapezium becomes indistinguishable from a rectangle. R is capital R is the radius of the circle, or the big circle, or the outer radius. So the radius of this big circle, and R changes from 0 to R. So Ri. Ri is the radius of each circle. So we go through, we add all of these circles here. We add all of these circles, and we have the integral. So as you make it the limit, it becomes the integral. And the answer is pi r squared. Ooh, interesting. So we used two different methods. Well, the same method, just different cutting, different slicing. We could further change that to a circle like this. And we can now split it like this into triangles approximately. This one is actually very easy because you take the area of one slice, area I, the ith area is equal to, if the angle is d theta, it's 1/2 d theta r squared. Well, r squared, because so it's 1/2 r squared d theta, and this ai is the sum of no, you can't use this formula because this for yeah, it's doing backwards. Yeah, okay, never mind. You can't use this formula because this formula assumes you already know the area of the circle, so it's working backwards. So no, you can't use that formula, but you can use the triangle. The area. This sector is approximately 1/2 r squared sine theta. Yes, it's approximately the angle of the sine theta. And for small angles, it's approximately 1/2 r squared theta. Interesting. And well, d theta, sine d theta and d theta. And then you have the sum of 1/2 r squared d theta, which is the integral of this, and just, yeah, from 0 to 2 pi. The angle changes from 0 to 2 pi. And okay, let's do this. Let's do it properly. Sine delta theta, delta theta, delta theta, delta theta, which is the integral of the okay, let's not simplify it. Let's leave it like this. Right. So where I'm coming from, this is a triangle. This is a triangle. It's an it is a isosceles triangle with sides r and the angle delta theta. It's not the height. I'm using the formula for the area of the triangle. Area is 1/2 AB sine theta. In this case, A is 1/2 R times sine delta theta. The angle is delta theta. So it is 1/2 R squared sine delta theta. So the total area is the sum of 1/2 R squared sine delta theta, which as is, well, the limit as delta theta tends to 0. So it's the integral of 1/2 R squared sine d theta. Aha, okay. Sine d theta. It does get tricky. What can you do here? Sine d theta. Can you do sine d theta? Well, sine d theta is, for small angles, we know it is 1/2 R squared d theta. I can even use the equal sign here because d theta is infinitely small. And when theta is infinitely small, it's equal to theta. And then you just integrate that between limits, the angle from 0 to 2 pi, because the circle is 2 pi radians across. So it's going to be 1/2 R squared multiplied by 2 pi. 2 cancels. It's pi R squared. Ta-da! Same thing. So another form of slicing. Okay. What are we? Quarter past. Find the center of mass of a semicircle of radius r. Okay, this is an interesting one. Find the center of mass of a semicircle of radius r. So what we need is a semicircle, of course. And we need to slice it. I'll just remind you the formula for the center of mass. X center of mass is the sum of xi mi divided by sum of mi. So we are going to slice the semicircle into bits. Mena, the mass of the fly is not negligible compared to the tube. I think they have equal mass, don't they? Let me have a look at problem. Physics. Yes, the fly has the equal mass to the tube. Tube of mass m, and the fly is mass m. So basically, you need to find the center of mass of the system, and then work from there. I'll talk about more maybe next week. You need to find the center of mass. The center of mass moves as a point object. And let's take the x-axis. The x-axis goes here, starts from here, 0 to x. This is the y-axis. And once again, let's say the mass density of the circle, mass density is sigma. So sigma is the mass of 1 square meter of the circle. Okay, so it's like a laminar mass density. Right. So the area of the strip area, strip I, let's call it strip I. AI, the area of the strip, is y, because this is the function, is y is equal to square root of r squared minus x squared, is y, 2y, I, because the height is 2y, delta x, I, and this is equal to 2 square root of r squared minus xi squared, delta xi. So where x is the position of the strip. So let's, for simplicity, let's say it's the middle of the strip. Now, mass of the strip, mass, is sigma multiplied by 2 square root r squared minus xi squared delta xi. And the total mass, total mass, well, it's just the area. Total mass is the sum of the mass, and which is equal to area, is pi r squared over 2. It's a half a circle multiplied by sigma. All right, so to find the center of mass, x center of mass, we need to use the sum of xi mi divided by the sum, so it's pi r squared over 2 sigma. We already know that. So sum of this, so it's the sum of xi multiplied by m, so it's sigma 2 square root r squared minus xi squared delta xi divided by pi r squared over 2 sigma. Now, approximately, I keep forgetting approximately, because this is a Riemann sum. This is not the limit. Now we take the limit of that. So x center of mass is the limit as delta x tends to 0 of this expression. Which is the integral pi r squared over 2 sigma from 0 to r x sigma multiplied by 2 square root r minus x squared. We don't need I anymore. And delta becomes d dx. Right. So what do we do with this? Well, first of all, we can get rid of sigma because sigma is a constant. We take sigma out and we cancel it. All right, that makes life slightly easier. So I'm going to switch this round. So it's going to be 2 divided by pi r squared integral from 0 to r 2x square root r squared minus x squared dx. And now this is a substitution, very clear substitution. So u equal r squared minus x squared. Du dx, we differentiate that and it becomes minus 2x. So dx is du divided by minus 2x. We sub that in. So 2 divided by pi r squared, integral from 0 to r, 2x multiplied by square root of u multiplied by dx, which is du divided by minus 2x. Ooh, beautiful. Cancel, cancel. And, aha, forgot one thing. Very important. I have to change the limits as well. The limits are now u1 and u2 because I've changed the variable. So u1, we substitute 0. u1, it becomes r squared minus 0 squared. So u1 is r squared. And u2 is we substitute r squared. So r squared minus r squared, so 0. So it's 2 divided by pi r squared. There's a minus here. So it's minus u to the power 3 over 2 divided by 3 over 2 between limits r squared and 0. So we take this out, so it's going to be 4 divided by 3 pi r squared, and then minus 0 plus r squared to the power 3 over 2, which is 4 divided by 3 pi r squared multiplied by r cubed. This cancels, and we get 4r divided by 3 pi. And this is the position of the center of mass. So if you have a semicircle, then the center of mass is at a distance of 4r divided by 3 pi from the edge, because we sent from the center of the imaginary circle, center of the circle. This is a very practical result. So if you take a semicircular disk, you know where you can balance it. Okay, so if the radius is, I don't know, 2 meters, if radius is 2 meters, let's just get a then 4r, so x center of mass is going to be 4r divided by 3 pi. So it's approximately 8 divided by 3 pi. So 8 divided by 3 pi, 0.84, 0.84 meters, which kind of makes sense. Yeah, so if you take a semicircular disk of radius 2, so this is 2 meters, the center of mass is going to be about 0.84 meters. Very reasonable. So I can see that it's likely that we haven't made a mistake. Now, looking back at problem 4, do you think you would be able to do the same problem from scratch by yourself on a scale of, no, not a scale, just 0 or 1? Yes or no? Just be honest, please. Do you think you would be able to do it now? You don't like you don't like discrete values. You get it wrong. Change the limits when yes, substitution. But no, but you do you think you can do it now? Like you've seen how I do it. Would you be able to repeat what I've just did? Ah, yeah, that's a good point. Have I I can't believe I haven't put that in the assignment. That would be very naughty of me. Changing the limits. Ooh, it does seem. There's no mention of it. That is true. Okay. I will make a point. I will make a point of that. Substitution, integration by substitution. Integration by substitution. Change limits. Well, you would get the opposite sign. You would you would actually, it would be a very small mistake. You would get a negative sign for the answer. But yeah. Still, there's 18 of you. I'd like some answers. Do you think you'd be able to do this exact question after I've shown you how to do it? Yes or no? 1 or 0? Please let me know. Okay, mostly ones. All right. Okay, very good. Find the center of mass of a hula hoop. It's a very similar question. It's just a different technique of doing it. So we take, and I was looking up the solution to this one, and I found a different solution which I didn't like, so I had to design my own solution. So same idea. So x, let's say we're somewhere here, we're at position xi, and we take the mass located at this coordinate, because of course the center of mass is somewhere along this line, along the x-axis. So what are those masses? What is mi? Mi is the combined mass, right? So let's look at it closely. So let's say we take a part of the circle. So here, what is mi? Well, mi is equal to the length. Let's call it dl. The length mi is dl multiplied by mu, where mu is the mass per unit length. It just mass depends on the length, and it's proportional to the length, of course, dl. Now dl is at an angle, and you can use Pythagoras. So this is dy and this is dx. So dl is square root of dx squared plus dy squared. And because it's a circle, you already know that y is equal to square root of r squared minus x squared. So we found y is equal to r squared minus x squared. So we find dy, well, dy dx, we use the chain rule here. We use the chain rule, and it's going to be minus 2x multiplied by 1 over 2 square root of r squared minus x squared. 2 cancels, and we get minus x over square root of r squared minus x squared. That means dy can be expressed as minus x over r squared minus x squared square root dx. And we use this to find dl. dl is square root of dx. I'm just going to speed up a bit because I want to do the more exciting problem, the next problem, which is more exciting, plus x squared over r squared minus x squared. So I'm squaring it, and dx squared. I take dx squared out, so where I'm left with 1 plus x squared over r squared minus x squared dx. Because I've taken dx out of the brackets and out of the root, and it becomes so r squared minus x squared plus x squared. I found the common denominator, divided by r squared minus x squared dx. X squared cancels. Square root of r squared becomes r squared minus x squared dx. Okay. So now we can find the mass. We can find the mass mi. Oh, sorry, I forgot to mention there are two of them. There are two of them. They're symmetrically placed, so one above, one below. So we need a 2 here. So mass is 2 multiplied by d multiplied by mu and multiplied by dl, and dl is r divided by square root of r squared minus x squared dx. Right, so this is m, and total mass is the length multiplied by mu, and the length is pi r mu. Pi r is the length because it's a semicircle. The length of the semicircle is pi r. Pi r mu. This is the total mass. And now we need to find the center of mass. X center of mass is the sum of xi mi divided by sum of mi. So sum xi, so x multiplied by 2 mu. Well, it's the limit delta x tends to 0. So we can straight away go to the integration. It's the integral of xi, so x multiplied by m, which is this, 2 mu r divided by square root of r squared minus x squared dx divided by sum of mass, and the sum of mass is pi r mu. And the limits of integration are from 0 to r, because we're going from the beginning, it's from 0 to r. Okay, so what is this? So 2 mu r, we take it out, 2 mu r, and we're left with the integral of x divided by square root of r squared minus x squared dx divided by pi mu r. So mu r cancels, regular 2 divided by pi. The integral of x square root of r squared minus x squared dx. Okay, and we need a substitution here. So u is r squared minus x squared. So du dx, we differentiate and it's minus 2x. So du is, well, dx, we express dx is du divided by minus 2x. We plug that in. So it's 2 divided by pi integral mi. It's the length times mu. Simply, it's length times mu. And the length is pi r times mu. Oh, length is pi r because it's the length of the semicircle. Does that make sense? And the integral of, so x divided by square root of u 0 to r, and with dx which is du divided by minus 2x, x cancels, 2 cancel, minus, so it's 0 to r. We need to change change it again, but it's the same principle. When it's 0, it's r squared and 0, and it's going to be minus 1 over pi, because there's a minus here. Now, it is u to the power minus half, so it's u to the power half divided by 1/2 between limits r squared and 0. And that is minus 2 over pi 0 minus r squared to the power 1/2, which is 2r divided by pi. Because I've taken this 2, 1/2, I've taken it and put it here. The 2 goes up, minus 2 pi, the 2 pi r, 2r over pi. This is the result. So if you have a hula hoop and you cut it in half, the center of mass is here, which is, this is the center of the circle. This is 2r divided by pi. And once again, for a 2 meter, if the radius is 2 meters, so the center of mass, x center of mass, is 2r, 2, so 4 divided by 4. It's approximately 1.27 meters. So it's, well, a bit further past, and that makes sense because there's a lot of mass here. There's a lot of mass here and less mass on the left. So yeah. Makes sense. Finally, we get to the last problem. It's different. It's completely different. It's very similar to this problem. Actually, this problem was, I think it was inspired by this one. I don't remember exactly where this problem came from, but this is a toy. This is called a Nevalashka, or it's called a roly-poly toy or a tilting doll. So this is how it works. This is the doll. This is the Russian variant, which scared me to my core when I was 3 years old. Okay, almost as scary as a clown. So you let go of the doll, and the doll doesn't fall down. And let's take a snapshot here. We kind of need to figure out where the center of mass is of the doll. And of course, this is a sphere. This is a sphere. And this is the point of contact. So this is the contact. And if you draw the vertical line, the center of mass has to be somewhere along this line. So the center of mass has to be anywhere here. Okay, so a likely position of the center of mass is, let's say, here. Because if the center of mass was here, it would fall over. If the center of mass was here, it would, well, it wouldn't come back to its original position. So the center of mass has to be to the left of the point of contact. So this is a diagram. So mark an X at the possible position for the toy center of mass. So from this position, the toy comes back to the standing. So it has to be somewhere here. And so this is the likely position of the center of mass. So here the center of mass is directly above the point of contact. Here is to the left of the point of contact, so it returns. And here it's once again to the left of the point of contact, so it returns to the original position. No, the center of mass does not move if the object is tilted. No, the center of mass is fixed with respect to the toy. Now, if you change the shape of the toy, then the center of mass moves, of course. So let's say you have a piece of rope, and the center of mass is here. Now, if you fold the rope in half, the center of mass moves to here. But if you don't change the shape, the center of mass doesn't change position. Also, here you can see that the center of mass moves up. That's another reason for the toy to return to original position, because it has less energy when it's upright, because the center of mass is lower. And any system will always go to the position of lowest energy, if it can. Right? Like you, if you stand on your tiptoes, that's inconvenient. You have too much potential energy. You don't like it. You'd much rather sit down and have lower potential energy. And if you're sitting down, you'd rather lie down, because then you have even less potential energy. So any system, including you, including the sun, including toys, including anything you can think of, always tries to occupy the state of lowest energy. And this is a very philosophical thing. I love it. It's the second principle of thermodynamics. It's the consequence of the second principle, second law of thermodynamics. It's quite cool. if you start thinking of systems as if they are living things, but they obviously are not, but they still obey the same rules. Okay, so what is the problem? The problem is a roly-poly toy with a rough bottom, so that means it is not smooth, it's rough, so it means it can stay on stay still on a slanted surface. Radius of 6 centimeters, height of 21 centimeters, mass 300 grams. If you place it on an incline, the toy is in stable equilibrium with its axis tilted at 45 degrees. Ooh, interesting. So I'm gonna try to use this picture. Is that 45? Does that look like 45-ish? Tilted at 45 degrees. Okay, so if the toy is at an incline of 30 degrees, so we've tilted the table. Or tilted the table. And at 30 degrees. 30 degrees. And the toy is now in equilibrium with its axis tilted at 45 degrees. 45 degrees. How much blue tack do we need to put at the top for it to lose balance? Well, I think it all boils down to finding the center of mass of the toy in the first place, because that's what we don't know, and that's what we are probably interested in. Even if I don't know how to do the whole thing, I probably want to find the center of mass. So we need to find the center of mass. Let's say the center of mass is here. Let's say it is a distance d away from the bottom. Now this is the center of the sphere, and this is the point of contact. Now, because the toy is in equilibrium, where is the center of mass with respect to the point of contact? If we cut the toy's head off, the center of mass moves. Yes. Yeah, I was scared enough by the toy itself. Now you want to cut its head off. Where is the center of mass with respect to the point of contact? Have a think about it. Axis tilted at 45 degrees. Well, look, we've put the table and we've slanted the table, and the toy, we tilted the table by 30 degrees, and the toy tilted 45 degrees, and now it's in equilibrium, so it doesn't move. Yes, Archie, thank you. It's perpendicular to the point of contact. Well, I'm not sure what you mean by perpendicular, what you mean exactly, but it is. It is directly above the point of contact. Now, because if it was to the left, the toy would move to the left and the angle would not be 45 degrees. And if it was to the right of point of contact, it would move further back, it will tilt further and will not be 45 degrees. If it's exactly 45 degrees, the center of mass is directly above the point of contact. Toy is in equilibrium. equilibrium. That means center of mass directly above point of contact. And now we use geometry to figure out D. So D is the distance from the center. This is R. And if we draw another vertical line here, and draw a horizontal line here, and a horizontal line here. Okay, so I'll have to increase that. I have to make it bigger. Yes, because there's no torque through around the point of contact. There's no moment. There's no moment around the point of contact because the force goes through the point of contact. Therefore, it won't tilt. So we will have to draw this. So this is D. This is like this. This is like this. This is like this. So what I have drawn here, this is the radius of the toy. So this line, this is this line. Now this line. Now this line is R minus D. Radius minus D, because this is D, this is R, and this is R minus D. And using triangles, hopefully somebody will not. I really hope you haven't lost me. You can see that these blue lines are the same. And this angle is 30 degrees. And this angle is 45 degrees. So R multiplied by sine 30. This is R sine 30. And this is R minus D multiplied by sine 45 is equal to R minus D multiplied by sine 45. And sine 30 is 1/2, so R times 1/2. And this is R minus D multiplied by square root of 2 over 2. 2 cancels, and we rearrange it. R divided by square root of 2 equals R minus D. So D is equal to R minus R over square root of 2. So it's R 1 minus 1 over square root of 2. Square root of 2 minus 1 over square root of 2 R. So that's the position of the center of mass. So the center of mass is a distance D away, and D is square root of 2 minus 1 over square root of 2 R. This is the result that we got. We got this result by realizing that when it's tilted, the point of contact and the center of mass have to be on the same vertical line. And then we use trigonometry and geometry to work it out. The triangles are here. So I'm just gonna draw them here to make more, hopefully make more sense. This is the first triangle. And this is the second triangle. And just label them A. This is the center. This is C, and this is B. This is A, this is C, this is O, this is B. I really hope that makes some sort of sense. So this is D. So this is the toy, this is the circle, this circle. Oh, okay. Does that clarify things? Or does it make it even more confusing? I mean, okay, look. It's okay if you don't fully understand how I did it. Do try to go through it by yourself and realize it. The point is I'm trying to make, I found the center of mass of the toy. By looking, from these data, I have found the position of the center of mass of the toy. Now, I want to add some, so this is the toy, and this is the center of mass. So I know that this distance is D, and this distance is R. So this is D, and the whole thing is R. I want to add some blue tack to this point, and I want it to lose contact. Effectively, I want to move the center of mass from this position to the center of this sphere. So what do we have? Well, we need an x-axis. We need an x-axis, and we have a sphere, and we have the toy's head, right? So let's say this is 0, this is R, and this is H. This is the length. Well, we already know that, okay. We know that the center of mass of the toy is here at distance D. This is the center of mass of the toy. And the mass of the toy is M. We want to add some mass, M small, but the center of mass has to now be at point R. So current center of mass is at x equals D. We want to move it to x equals R. So we want to add some blue tack to the top in order for the center of mass to move from this position to the new position here. Because then the center of mass is above the point of contact and it will topple over from any position. Okay, so how do we do that? Well, we find the center, we use the formula for the center of mass. Center of mass is x1 m1 plus x2 m2 divided by m1 plus m2. And we substitute what we already know. x1, the position of the center of mass of the toy, that is D, multiplied by m1, which is m, plus x2. This is the position of the blue tack, so it's h, multiplied by m, which is the unknown mass of blue tack that we need, divided by m plus m, and that has to equal to R. Well, we need the minimum amount of blue tack. Okay, I need to specify that. What is the minimum? Thank you. Minimum mass of blue tack needs to be added to the toy, to the head, to the toy's head for it to lose balance on a horizontal table. And of course, if you add blue tack somewhere else, someplace else, you would need more of it. So you don't even have to say toy's head. But anyways, and this has to equal to R. And now we just substitute what we already know. So D is square root of 2 minus 1 over square root of 2 times 6 times M, which is 300, plus H is 21, I believe. 21 multiplied by M divided by 300 plus M equals R, which is 6. 6, seriously. That's a very small radius. Okay. 6, okay, and then we just work it out. Square root of 2 minus 1 over square root of 2 multiplied by 1800 plus 21m equals 1800 plus 6m. No, because I'm using I'm being consistent. I'm using centimeters and grams, so it doesn't affect anything. Oh, my answer is going to be in because the top is gram centimeters and divided by grams. Gram centimeters divided by grams is going to be centimeters. So this is gram centimeters, and this is gram, and this is going to be centimeters. So there's no contradiction here. I'm being consistent. So one thing I'm usually quite good at is not messing up the units. What can we do? So multiply by square root of 2 just to okay, yeah, multiply by square root of 2. So it becomes square root of 2 minus 1 times 1800 minus 1800 plus 21 square root of 2m equals 1800 square root of 2 plus 6 square root of 2m. Okay, m 21, so 15 square root of 2m equals would you look at that? That's good. It's always good. Equals 1800. So m is 1800 divided by 15 square root of 2, which is 1800 divided by 15. 120. 120 divided by square root of 2. So it's approximately 60. Well, it's equals 60 square root of 2, which is approximately 84.9 grams, which sounds reasonable. Just a quick sanity check. Well, yeah, if it's a 300-gram toy and the center of mass is here, if we attach about 80 grams to the top, the center of mass is very likely to shift to this position, and then the toy will lose stability, will just topple over. Okay, so hope that makes sense. I hope you enjoyed the last problem with the toy. At least, I mean, it had different layers. It has many different layers. First, we talk about the center of mass of the toy and why it doesn't topple over, and then we tilt it, and it tilts further, and by finding that tilt, we can find the center of mass. And if we find the center of mass, we can find how much blue tack we can put at the top for it to become unstable. Finally, this one, it's the same thing. I mean, the center of mass, you need to find the center of mass, and the center of mass will be directly above the point of contact. This point of contact, because only then it can be stable. Now, if we keep tilting it, at some point, it will become horizontal, and from that position, it will just roll over. If we keep tilting it, it will be in this position. The center of mass is here. The point of contact is here. And if you tilt it any further, there's nowhere else for the system to tilt, so it will just roll off. So it's just simple geometry, reasonably simple geometry. There's a lot of very complicated physics followed by some reasonably complicated geometry. So give it a go. I mean, it's not that hard of a question. It sounds much harder than it is. And of course, if the friction is low, then it will just slip off. So it would slip off without reaching the point of where it can roll. When finding the initial of the length g, do we need to consider anything? No, because that's the beautiful thing about it. The position, it doesn't even matter. The shape of the toy doesn't matter. As long as you know that it tilts by 45 degrees, you can work out where the center of mass, because the center of mass is always above the point of. If you are in equilibrium, the point of contact is on the same vertical line as the center of mass, always. Because otherwise there would be a moment turning it this or the other way. That's what you need to understand. So if you're stable, if you are not moving, then point of contact, center of mass, or point of contact, center of mass. It could be above or below, or it could be at the same point, but it's on the same vertical line. And if the center of mass is above, it's unstable equilibrium. If it's below, it's stable equilibrium, and at the middle, it's yeah. So that's about it. So I hope you enjoyed today, and I'll see you next week. All right. See you all.